Remember that when a ketone or aldehyde reacts with an alcohol in the presence of acid, you're going to get acetals and hemiacetals. Okay? And remember that the difference of whether you get a hemiacetal versus an acetal a lot of times just has to do with the number of equivalents of alcohols that you're using. So remember that in the first equivalent, you're going to go from your ketone or aldehyde to your hemiacetal, also known as your half acetal. That's what hemi stands for. And that means that you're forming a functional group that has an OH on one side and an OR on the other. That's a hemiacetal. Then remember that when you react that hemiacetal again with another equivalent of alcohol, what you're going to get is now a full acetal where you have OR groups both connected to the same carbon. Okay? In this video, we're just going to try to remember the hemiacetal mechanism because I have another video for the acetal mechanism. Okay? So in this video, we just want to review how do you go from that first step of adding one equivalent of alcohol to the ketone or aldehyde to make the hemiacetal. So like any good acid catalyzed mechanism, the first step always starts off with protonation, right? So the O grabs the H and kicks electrons down to that O, and now we get a set of resonance structures. So that means I'm going to have an H here, I'm going to have an H here, and what else are we going to have? Well, we're also still going to have this double bond here and a positive charge. Now this is where resonance comes in. This positive charge has a resonance structure where this bond can come up here and give electrons up to the O, which means that the other resonance structure of this cation looks like this. Cool? So you have those two different cations. Some professors skip this step, but I like to draw it. You don't have to necessarily draw it, but I like to draw it because it shows you where to put the alcohol in the next step, which is a nucleophilic attack that adds right here to that cation, okay? So then we add that there. What that means is that now we're going to get ROH down here with a positive charge because now it has too many bonds. And we're still going to get this alcohol that was formed in the first step. Lastly, we're going to use an equivalent of alcohol to go ahead and deprotonate that OR group. And what we're finally going to get is our hemiacetal, which is OH, OR, and I see that I have an OH and an OR attached to the same carbon. That is the same as the hemiacetal that I have drawn there in the middle. Okay? Now, a few other things before we end this video. Remember that it turns out that even though you can make a hemiacetal with one equivalent of alcohol, most acid catalyzed mechanisms are going to proceed forward all the way to the acetal. They're not going to stop because most reactions have excess alcohol in them. So as long as you have the extra alcohol around, it's going to want to react twice, not once. It's not just going to want to stay at the hemiacetal. It will go all the way to the acetal. So you're thinking, how do I make sure that it will be a hemiacetal then? Well, the only way to really make sure that it stays as a hemiacetal is to make it a cyclic hemiacetal. If you can form a ring with that OR group, then it can end at the acetal, at the hemiacetal, and this would be our example over here. How notice that my carbonyl carbon actually was this one. This one is attached to an OH at the top, an OR at the bottom, and that means if you have an OH and an OR, I'll just go ahead and highlight these to make it even more obvious. If you have an OH and an OR attached to the same carbon, then that is a hemiacetal, since it's forming a ring that's a cyclic hemiacetal, which is the only stable form of hemiacetal. If you're not getting a ring at your hemiacetal step, you're probably going to have to go ahead and draw the second step, which is the acetal. All right, so that was it for this summary video, but for more information on hemiacetals, feel free to go to the concept video.